Okay, folks, here we go again with another marvelous session of pre-calculus on the topic of trigonometry. Hello. Hopefully I can get through this without any blunders. Two announcements. One is please watch out for mistakes I might make. If you see me do something wrong, since I don't have you guys out there to flag me down and say, "Oh, Mr. Pear," just email me as quickly as possible if you find a mistake, and I will send out a correction, not a correction video, but a correction text or email message. Secondly, I am intending to cease posting assignment descriptions on RenWeb. For one thing, it'd be easier if I don't. But also, if I don't put it on RenWeb, that kind of encourages you to actually watch the videos, because I will describe the assignments and write them clearly on the board. So without the video, you don't know what the assignment is. So that will encourage you to actually watch the videos, which I'm confident you already are doing, but I'm just trying to, add another layer of security. I'm hopefully going to be able to get through today's material without any blunders. I will frequently look at the book to make sure I'm not saying anything silly. We move on. We're now going to be looking at the Pythagorean theorem, or Pythagorean identities based on the Pythagorean theorem. What is that on my back? Hi. Sorry, folks. I think it's a chicken pandemic. They're all over the place. What was I doing? I don't know. Wow. Okay, consider this. Going back to some old stuff here. Unit circle. Unit circle again mean that the radius is 1. The coordinates of this point, because we're calling this x and this y, then the coordinates of this point are clearly x, y. And by definition, the sine of theta is y, the second coordinate. And the cosine of theta is x, the first coordinate. This gets cool. Watch this now. We also know, the Pythagorean theorem, that in any right triangle, that in this case, x squared plus y squared has to equal the hypotenuse squared. Well, a unit circle, 1 squared. Get out the calculator? Yes, 1 squared is 1. But hold on just a moment. Isn't x the same thing as cosine? So I can change this x into cosine of theta. And I can change this y into sine of theta. And there we have a very important trigonometric identity that you have to memorize, but it's not hard to remember. And that is that cosine theta squared plus sine theta squared equals 1. A critical, fundamental trigonometric identity that you have to know. By the way, to simplify things, we do not normally write this as cosine theta squared. We write it in a way that perhaps logically makes no sense, but it's the way it's done. We don't write cosine theta squared, we write cosine squared theta. So this, I would have to agree that this makes no mathematical sense in itself, but we simply understand that this is a shortcut way of writing that. So we'll write cosine squared theta plus sine squared theta equals 1 is one of our fundamental trigonometric identities. And if you can remember it simply by remembering it's based on the Pythagorean theorem. It's that would be your a squared plus b squared equals c squared. Or in the case of the unit circle, x squared plus y squared equals 1 squared. Pretty easy to remember. Now, there are times when you'll want other forms of that. For instance, there may very well be times when you would prefer to think of it as solving for sine squared. And you would have the fact that sine squared theta equals 1 minus cosine squared theta. Why do I always run out of room on the right side of the board? Let's move this over. There we go. Okay, so yeah, sine squared theta equals 1 minus cosine squared theta, simply subtracting cosine squared theta from both sides. We could do the same thing. We could write cosine squared theta equals 1 minus sine squared theta. So these things should be immediately obvious to you once you have this firmly in your psyche. Now consider this. We're going to do something kind of interesting here and generate another fundamental identity that you have to have memorized. It's one that you could easily recreate on your own, but why go to the trouble of recreating it if you have it memorized? We're going to take this equation. We're going to divide both sides by cosine squared theta. Is that the one I want to do first? We're going to go in the same order the book does. Yes. We're going to take this thing, and by the way, I'm noticing the book more commonly writes this the other way around. They more commonly write it as sine squared theta plus cosine squared theta equals 1. I'll stick with the normal convention of putting the sign first. Just flipping those two terms around. Now we're going to take this guy. We're going to do something pretty cool to it. I think it's pretty cool. We're going to divide both sides of the equation by cosine squared theta. Why would you do a thing like that? Oh, just watch what happens if I divide both sides of the equation by cosine squared theta. Really cool things happen. First of all, remember that sine of theta over cosine of theta equals tangent of theta. So does it make sense then that sine squared theta over cosine squared theta will equal tangent squared theta? So we're simply going to replace this guy, sine squared over cosine squared. We're going to replace that with tangent squared theta. Plus, cosine squared theta divided by cosine squared theta. Mr. Bear? Yes. Have they changed any of the old rules we learned in elementary school? No, they have not changed the old rules. Well then, a number divided by itself should still be equal to 1, right? Well, of course. So we can change this to a 1. Now over here, this is the reciprocal of cosine squared, isn't it? Well, guess what the reciprocal of cosine squared is? Remember our sine, cosine, tangent, cotangent, secant, cosecant, and the reciprocals. So the reciprocal of cosine is secant. So this simply becomes secant squared theta. Pretty cool. Tangent squared theta plus 1 equals secant squared theta. That will come in very handy. That's one that you need to know. I'm going to show you, by the way, a trick that will make it a little bit easier to remember this. But not quite yet. We'll get there momentarily. Let's back up now to tell you what. Let's get fancy here. I'm going to take this guy and just kind of move it down there out of the way for a moment and go back to the beginning. Starting with sine squared theta plus cosine squared theta equals 1. You might be able to guess what I'm going to do next, or maybe you can't. We just found out what happens if we divide both sides of the equation by cosine squared theta. We get that, which is pretty cool. Well, now we're going to take that same equation, Pythagorean theorem, a squared plus b squared equals c squared. And we're going to divide both sides not by cosine, but we're going to divide it by sine squared theta. Divide by sine squared theta plus, sine squared theta and sine squared theta. All right, well, here, sine squared over sine squared is just going to be 1 plus, what's cosine over sine? We know what sine over cosine is. Sine over cosine is tangent, of course. That's old. That was from last week. So flip that, make it cosine over sine. It must be 1 over tangent. But what's 1 over tangent? 1 over tangent is cotangent. So this gives us cosine over sine must be the reciprocal of sine over cosine, so it must be the reciprocal of tangent, so it is cotangent squared theta equals. And then, what's the reciprocal of sine? Reciprocal of sine is cosecant, so this becomes, cosecant squared theta, and there we have another identity that you have to know. Let's do one little trick here to make this easier to remember. Let's flip this around. Cotangent squared theta plus 1 equals cosecant squared theta. Now, I told you I was going to give you a way to help you remember these. Here it is. If you can get embedded in your head the general look of this, okay? We've got a function squared plus 1 equals a function squared. We have a function squared plus 1 equals a function squared. How do you remember what goes in the blank spots? Here you go. Cotangent goes with cosecant. Just plain tangent goes with just plain secant. Cotangent with cosecant, just plain tangent with just plain secant. That may help you remember these two. So that gives us now 3 of these Pythagorean theorem identities. Identities are based on the Pythagorean theorem. And that would be these two plus sine squared theta plus cosine squared theta equals 1. So these 3. In addition to all the obvious ones, I say obvious, the old ones like the fact that sine theta is 1 over cosecant theta, and all those reciprocal functions. Was there something else I'm forgetting that we need to remember? Oh, and of course the fact that tangent theta equals sine theta over cosine theta, and the reciprocal of that being that cotangent theta must be exactly the reciprocal of this one, because tangent, cotangent are reciprocals. So that gives us cosine theta over sine theta. So these guys must all be known. All of the reciprocal functions, as well as tangent theta being sine over cosine, and cotangent being cosine over sine. And then these 3 guys, all of these are fundamental identities that you have to know. That you have to know. Yes, there are some things in this class that have to be memorized. This is one of them. But I would dare suggest that once you get used to them and practice them a little bit, and think about the patterns you see that I've already pointed out to you, these should not be too horribly difficult to remember. If I had just thrown these at you a couple of weeks ago, you would have been kind of lost. But now you see where they come from, you see the patterns, and you realize, yeah, I can make sense of this. Yes, I can remember these. Yes, I'm going to have to take some time to sit down and actually memorize them, but there are enough patterns and hints along the way that I should be able to memorize these with very little difficulty. Now, I don't know how I'm going to do it yet, but traditionally I've given a quiz where you simply have to write down all of these identities with a few promptings on paper. I don't know how I can do quizzes in this format. I may create a Google Classroom quiz. Then again, I may not. I don't know. I'm still thinking that through. But we move on. Now, let's see, that covered. By the way, these are all summarized for you in the middle of page 379, that yellow box right in the middle that says fundamental identities. There they all laid out for you in the book, as well as here. You know, research has shown that if you actually write something down, you're going to remember it far, far better than if you just see it. If you just see it, it's in there for a few moments and then it's gone. But if you write it down, it gets embedded in the brain. So in other words, I would encourage you, I wish I could demand it of you, but I can't from afar. But I would strongly encourage you to actually write these things down, even though they're here for you. Let's be honest. When are you going to go back and look at this video again? I would like to think that you look at it multiple times, but let's be realistic. This may be the last time you see it. Yes, it's in the book. That's wonderful also. But you need to write it down, and you need to practice writing it down without the book and without the video. And then check yourself and make sure you did it right. The more you write it out, the better you're going to remember it. All right, we move on. Let's see. Oh, these are fun. Consider this. I'm now looking at the bottom of page 379, and it is, by the way, a very good idea for you to follow along in the book. Theoretically, you have your book at home with you, and you should be following along on page 379. We're at the bottom at example 4, which is where things get really fun. It's kind of like a puzzle, but these puzzles are easy. Tangent of 20 degrees minus sine of 20 degrees over cosine of 20 degrees. We're supposed to evaluate that without a calculator. And let me give you a hint. It should take you approximately, maybe 4.7 seconds to figure this out in your head without a calculator. No, it's only if you're a genius. No, really. You can do this by a cute little trick. Notice, please, that they are all 20 degrees. So that's just like having a theta there. What's sine theta over cosine theta? What's sine of 20 over cosine of 20? Is not sine of theta over cosine of theta simply equal to, tangent of theta? That means that this really says tangent of 20 minus, tangent of 20. Mr. Fair! Yes? Isn't that just 0? Yes, it is equal to 0. This is equal to 0. Because you've just got tangent of 20 minus tangent of 20. And tangent of an angle minus tangent of the same angle is, of course, 0. Nothing to it. Let's look at the next example here. Next one they give you is this. A little more interesting, perhaps. Sine squared of pi over 12. Of course, that previous example was in degrees. This is in radians. How do we know it's radians? Well, the pi is a hint that it's radians, but that's not proof that it's radians. Remember, for degrees, we use the... Okay, I thought I saved that. Where'd it go? I hit the wrong button. Did I not save it? I thought I had it. Oh, there it is. If we're using degrees, you use the degree sign. If there is no degree sign, which, by the way, sometimes I forget to do. If there is no degree sign, then it's implied, not implied, it's by the rules of trigonometry, that means it's radians, because there's no degree sign. Degrees are not radians. Radians are not degrees. If we're doing degrees, we talk in terms of degrees. If we're doing radians, there is no degree sign. Anyway, actually that's totally irrelevant in this example. We don't care if it's radians or degrees. It doesn't matter. Moving on, because this example says we're going to add to this 1 over secant squared of the same thing. All right, and we're supposed to simplify that without a calculator. This one might take, instead of 5.7 seconds, this one might take 8.3 seconds perhaps. Here's the trick. Isn't secant the reciprocal of Okay, think it through. Sine, cosine, tangent, cotangent, secant, cosecant. Do your little brackets. Oh, yes. Secant is the reciprocal of cosine. So this is nothing more than sine squared of pi over 12 plus the reciprocal of this being cosine squared of pi over 12. And we know that sine squared theta plus cosine squared theta. What is sine squared theta plus cosine squared theta? Do I still have it here anymore? Nope, I've deleted it. Oh well. But sine squared theta plus cosine squared theta is simply 1. Pythagorean theorem. A squared plus b squared equals c squared. In a unit circle, c is 1, so there we have it. Done. Well, that was kind of neat. Yeah, I think it's neat. It is really cool. Now, here's an interesting thought. I feel like I showed you this before, but I guess, no, I did not. Okay. Let's, I'll try to save that. Let's start again with sine squared theta plus cosine squared theta equals 1. By this time, you should already be getting used to this to the point where you could, who needs it? You know what that says. It says what? Sine squared theta plus cosine squared theta equals 1. Pythagorean theorem. All right, now, we're going to do this, some kind of interest with this. We're going to solve for sine. We're not solving for sine squared, we're going to solve for sine. So your procedure, first, get rid of this guy. Sine squared theta equals 1 minus cosine squared theta. Nothing mysterious about that. An Algebra 1 student could do that, even if they don't know what this means. We're simply subtracting cosine squared theta from both sides. Now, how do we get rid of that exponent? Well, how about take the square root of both sides of the equation? That'll give us sine of theta. Notice, please, the exponent is gone. Sine of theta equals the square root of 1 minus cosine squared theta. Oh, Mr. Pearson, that's just going to be 1 minus cosine? No. You know better than that. Radicals don't work that way. That minus sign messes things up. It's not like the square root of 4 plus 9 is not going to be 2 plus 3. No, it's the square root of 13. So no, you can't split that apart. So we're stuck with that. But, when you take the square root of both sides of an equation, don't you have to consider both the positive and the negative square roots? Oh yeah, plus or minus. However, you know something? We don't really care. What determines whether we want the positive or the negative? That's determined by what quadrant we're in. So this is all students take chemistry. It tells us whether our result is going to be positive or negative. It depends on where your theta happens to be. If your theta is in the first quadrant, then you're going to take the positive. If your theta is in the second quadrant, all students take chemistry, then sign will again be positive. But if your theta happens to be in the third quadrant, then your sign will be negative. Or if it's in the fourth quadrant, your sign will be negative as well. It's all students take chemistry. So yeah, technically we need to have the plus or minus there, but if you simply remember that depending on what quadrant you're in, you have to remember to give your answer the appropriate sign, then you're okay. And don't try to take the square root of this. If you do, you've butchered it. All right, now, that's a fairly minor concept there. Let's look now at this. I'm now looking at example 5 on page 380, and it goes like this. Suppose I know that the sine of my mystery angle theta is exactly 1/3. By the way, unit circle. If the sine is 1/3, this is positive. Where is sine positive? Sine is positive in quadrants 1 and 2. All students take chemistry. So sine is positive here and here. So this angle, whatever the angle may be, it must be in quadrants 1 or 2. That much we know so far. But then they give us an additional hint. They tell us in this example that cosine of theta is negative. Well, where's cosine negative? Cosine is positive here. All students take chemistry. And here. It's positive here and here. That means it must be negative here and here. So what one quadrant fits both of these, where the sine is positive and the cosine is negative? We've got to be in quadrant 2. It's the only place where sine is positive and cosine is negative. We are in quadrant 2, someplace. That's important. Once we've established that, we draw ourselves a little triangle, a little right triangle here. We know the sine is 1/3. Interesting. Well, sine, think again in terms of so, ka, toa. I trust that by this time in your experience that everybody knows how to spell so, ka, toa. So, O-H, ka, A-H, toa. So, let's see, sine is 1/3. Sine being opposite over hypotenuse. So in this triangle, opposite over hypotenuse is 1/3. Now we need to figure out what this guy is. Now, of course, if this were a unit circle, I would have to divide by 3 and divide by 3. But I really don't care whether it's a unit circle or not. I can go ahead and let the hypotenuse this time be 3. Everything's going to work out just fine. So, how do I now figure out the missing side? Pythagorean theorem. A squared plus b squared equals c squared. Fill in the blanks. A squared plus b squared. Let's go ahead and call this guy x. X squared plus 1 squared equals c squared. Subtract 1. X equals 8. Oops, I'm sorry, x squared equals 8. Take the square root of both sides, so x is either positive or negative square root of 8. But yes, please, I do expect you to simplify radicals. Oh no, we don't remember how! Let's quickly review how to simplify radicals, old stuff from Algebra 1, reviewed in my geometry classes, and then again emphasized in Algebra 2, so don't tell me you've never seen it. Simplifying a radical, you ask yourself, what perfect square goes into 8? 4! That's right, 4 goes into 8. In your head, usually, you think 4 times 2. Do you remember the magic word when simplifying radicals? A word that's going to go into my book that I'm never going to write. Or a word that's going to go into my peer dictionary that I also am never going to write. That word is, I'm sure somebody in the room remembers it. Yeah, I heard that over there. You remember. It's the word pa-ching. Here's the pa-ching concept. I changed that 8 probably in my head into a 4 times 2. Why? Because I know the square root of 4. If I know the square root of 4, I can take it out. There's the pa-ching. That 4 goes pa-ching, pops out. And when the 4 pops out, pa-ching, it turns into its own square root because we're taking the square root of 4 and 2. So the 4 pops out, pa-ching, turns into a 2, don't forget the plus or minus, square root of what could not come out? Well, the 4 pa-chinged, the 2 does not. The 2 is the wrong shape to pa-ching. It's not a perfect square, so it's stuck inside. We have properly simplified our x value. Now, I would like to just glance in the book and make sure I haven't done anything really silly here. Oh yeah, the only silly thing I've done. We have to decide, is this actually going to be positive or negative? Well, we've already established that my angle is in the second quadrant. In the second quadrant, everything is positive here, and only sine is positive here. Well, what are we talking about? I don't know what we're talking about. Let's just look at the signs here. We can see clearly, because we're in the second quadrant, we can see that this has to be negative 2 square root of 2, because I'm going that direction. This has to be positive 1, and of course hypotenuse is always positive. So in this particular case, x is negative 2 square root of 2. Don't forget about your signs. You do have to consider signs. All right. What's our next example? That was example 5, and that's all there is to example 5. There is an alternate way to do this using identities. The book goes through that alternate method. It could be, I suppose, kind of interesting to... Oh, I forgot about one very important detail. In this particular problem, they give you these two facts, and they're asking you for all 6 identities. Well, obviously sine was given to us. Cosecant is easy, right? Cosecant is the reciprocal of sine, so cosecant is 3. Then for the others, once we have all this, we can just use either the coordinate method. The coordinates here are negative 2 square root of 2, comma 1, and you can either use sine, my brain just went right out the window. Oh, this is assuming it's a unit circle. It's not a unit circle, sorry. It is a unit circle. I'm losing myself here. I think I was trying to explain something in a way that's just not going to make any sense and is confusing me. So let's back up a second. If you want to use the alternate method, we would start with sine squared theta plus cosine squared theta equals 1. We already know what sine squared theta is. Sine of theta is 1/3. So sine squared theta is what? 1/9 plus cosine squared theta equals 1. Let's bring it down to 1. Subtract 1/9 from both sides. Oh, I hate fractions. Okay, get a calculator that will do fractions for you then. Casio FX300EX. By the way, somebody apparently borrowed my beloved Casio FX300ES calculator and must have taken it home forgetting that it was mine. If you happen to have a calculator that has my name on the back of it, please send it in, bring it by, drop it off at the office or something. I really do miss it. So cosine squared theta equals, what's 1 minus 1/9? Well, what's 9/9 minus 1/9? That would be 8/9. Then take the square root of both sides. So cosine of theta must be the square root of 8/9, which is, we need to simplify that. Sorry, we do need to simplify it. In your head, you think of it as square root of 8 over square root of 9. But square root of 9 is just plain 3. And square root of 8 is 2 square root of 2. Remember from the earlier example? 2 square root of 2. By the way, simplifying square root of 8, it comes up so often that if you don't already automatically know that it's 2 square root of 2, with some practice and some time, it'll become automatic to you. Just like we know that 5 times 6 is 30. Square root of 8 is 2 square root of 2. You'll just know it because you see it so often. You could very well already know it. So that's cosine. All right, we know what sine is. Sine was 1/3 because we were told it was in the problem. So now tangent is simply